Thank you all very much for being here. Particularly, I'd like to congratulate Bert for his illustrious career and the organizer for inviting me. Just following the Bert model, I'd like to have a little bit of applied catalysis and a little bit of fundamental catalysis in my talk that I brought today. So this is part of our effort in upgrading bio-oil. As you said, that this is an area that we've been working for several years now. As you have known for sure that the biomass could be very readily converted with fast pyrolysis. But of course the product that you obtain here is by no means a final fuel. So if you look at the GC of that, it has about 500 products. And one of the issues that I like to draw attention today is that if you look at this, that we always divide in three families: the small oxygenate, chlorophylls are acids, the sugar-derived furfural, and the final is the lignin-derived phenolics. You see about half of the mass is C4 or less. So if you try to take this and do hydrotreating, as many people are doing, or companies, you can get a product that is okay. However, you lose more of half of the mass is already lost in form of light gases, and the consumption of hydrogen is huge. So one thing that we've been developed in Oklahoma for the last few years is try to do fractionation of this during the process, during the pyrolysis. So if you do that at different temperatures, for example, if you take a torrefaction of the biomass and then you continue with the solid, resulting solid, and you do it again at a higher temperature, then you do it again at fast pyrolysis of what's left here. Now you're able to divide these three families into like oxygenates, sugar-derived compounds such as furfural, and the phenols. So now you're able to do different chemistry for different of these fractions. So for example, one of the things I like to go on today is that ketonization of the small acids can produce acetone. And acetone is a very nice building block in bio-oil production because you can do a low condensation and combine that with the furfurals, for example, making now ranges of molecular size that could be hydrodeoxygenated and go directly to the fuels. At the same time, you can use the lignin-derived phenolics to do the same thing. Now you can have a pool of fuels with larger molecular weight than when you started here. Another option is to hydrogenate the acetone selectively to isopropanol, and this is another work that we have done recently. So isopropanol is a very good alkylating agent that you can combine that with the phenolic before you go to the hydrodeoxygenation. But today I'd like to talk about this part. So in order to take the acids which provide the corrosivity of the bio-oil, and if you try to hydrotreat that, it will produce gases, we try to make carbon-carbon bond formation, so to make acetone, for example, from acetic acid. So things that are desirable would be to do the ketonization in the aqueous phase. Something that usually is not done. Ketonization has been done for many years in the vapor phase. And conditions that are moderate temperatures and pressures. So for that we looked at the catalysts that are more active at lower temperatures. So we saw that reducible oxides, mostly promoted with methods, they work well in the vapor phase. The question is, would be the same in the aqueous phase in the presence of water that will deactivate the catalyst. So in order to do that, we tested different catalysts, and the one that has been the best is one supported on activated carbon, on which we deposit titanium isopropoxide, so we can get very high dispersion of titanium. And on top of that, we put the ruthenium to have this pair of the metal with a reducible oxide. So we have done very good characterization by XPS and other techniques. So I'd like to talk a little bit about how this one behaves. Then I'll talk about some of the kinetics and some of the mechanisms that we have investigated. So one thing that you realize when you do X-ray diffraction is that the titanium is strained. So you have a very high dispersion of the titanium on the carbon. As you can see, This is the P25. There is a combination of anatase and rutile. Here is mostly anatase. And most interesting, you observe a significant shift there that may be related to the interaction of this very highly dispersed titanium on the carbon. So when you do high resolution TEM, you can see this one is like platelets of TiO2 that result from very high dispersion of this. And on top of that, we put the ruthenium. As you can see, some of the small particles that are sitting on top of the TiO2 platelets. So you expect a fraction of the ruthenium on top of the titanium, and of course another fraction on the carbon. So we're going to investigate the activity of the ruthenium on carbon, titanium alone, and ruthenium titanium to see which one is the most active species. So one thing that we have realized is that in order to be reducible, the support, you need to have a metal and hydrogen. So ruthenium by itself reduces relatively easily, and titanium, when the temperature is high enough, you can have some reduction, particularly in this case when it's supported on carbon. But when you combine ruthenium and titanium, you observe now that the reduction of titanium have moved to lower temperatures. So if you do some quantitative analysis of the TPR, you see that for the amount of ruthenium that we have in this catalyst, which is around 5%, integrated in this area, you see most of that will be necessary hydrogen to reduce the ruthenium, and you have all these left for the titanium. So there is a significant amount of titanium reduction, which similar to the talk that Hu gave before, the hydrogen spillover plays an important role here, so causing a significant reduction of the TiO2. So we have done SPS to show that this is in fact the case. So when you look at the titanium supported on the carbon, after calcination, everything is titanium 4+. But when you have the ruthenium causes some defect there. So even after calcination, before the reduction, you start seeing some titanium 3+ on the surface. And of course, when you reduce it, a very large fraction of the surface become reduced with very large concentration of titanium 3+. And you can see the shifts very clearly here in binding energy. The other question that we have is, well, now we're going to take this reduced material, we're going to put it in water. Will water oxidize the titanium? We lose everything that we started with. Well, in fact, no. We observe by EPR, this is a typical EPR of reduced titanium. So you have two contributions here. This G equals 2, that corresponds to absorb oxygen near the titanium 4+. But this one, the G perpendicular here, 1.9. So this one is due to this electrons trapped in the titanium 3+. So whenever you have reduced titanium, you should observe this. So what we observe here is that as synthesized, the ruthenium titanium before the reduction, you only observe the G equals 2, which correspond to Tr4+. However, after we do the reduction and we expose to the water, so if there was any oxidation or reoxidation which should go back here, we can observe that still a large fraction of reduced titanium remains. So let's see what happened with the ketonization activity, and then we're going to start talking about the mechanism. So this is a reaction that we want to accomplish. So we have acid in the bio-oil, for example, acetic acid, propionic acid, and so on. So we want to remove the acidity and increase the carbon-carbon bond change. So if we do that on ruthenium on carbon by itself, ruthenium is very inactive for this reaction. Essentially, we get no conversion. If we look at ruthenium on titanium, without any pretreatment, the activity is also almost nothing. Now, if you take titanium by itself and you do the reduction, even without the metal, you observe a significant increase in conversion towards acetone. But if you do that in the presence of ruthenium and hydrogen, now you are utilizing the ability of ruthenium to reduce the titanium around, you can see there is a tremendous increase in conversion and activity as measured here. Finally, when we look at the preferred catalyst, in which we have the TiO2 supported on the carbon, and that impregnated with ruthenium, we see even a further increase. So we have a very high activity catalyst with very high selectivity for the desired acetone. So here's a summary of this. So we have, while ruthenium by itself has no activity, so it is in the presence of TiO2, emphasizes the activity of TiO2 to produce very high rate for ketonization. So again, if you compare now the reduction or without reduction, titanium by itself gets a boost in activity when it's reduced, but when it's with ruthenium, this boost is even further. So the question now is, okay, from the mechanistic point of view, what causes that whenever we do some reduction here, or we produce some oxygen vacancies, are we emphasizing the activity for ketonization? So the next would be to investigate what is the mechanism of that. So the first thing that we need to realize is we are doing this as opposed to most of the previous studies in the liquid phase, in the presence of water. So the surface will be covered by water. Reduced or not, we expect to have absorbed water on the catalyst. But there are some calculations here that they show that when you have a carboxylate, as here, there is preferential absorption when we, even in the monodentate form, when going from a surface completely covered by water with one in which the carboxylate gets absorbed. And even more, when you take this monodentate carboxylate and that goes to the bidentate carboxylate, so the drop in energy is significant. So there is a possibility now for the carboxylate to compete very effectively with water. So let me study a little bit what has been done so far in the ketonization reaction, which is a reaction has been very well studied in the vapor phase. So one of the mechanisms that was proposed many times is via ketene. So what is considered is when we have the two acids here, so an alpha hydrogen, which is the carbon next to the carbonyl here, will react with OH, producing the dehydration of this molecule, forming the ketene. So this ketene is very reactive, and the ketene will react with another molecule, mostly from the gas phase, producing the ketonization. This was proposed a long time ago and has been further proposed by other authors. However, there is some problem with this, because if you realize that if we are removing this oxygen here, it means that the CO2 that we are producing will not come from the molecule that contains the alpha hydrogen. So there have been studies like, for example, Nagashima and Sato, in which they have this propionic acid combined with the different carboxylic acid, and look at the ketonization product. So, for example, the propionic acid by itself will produce a pentanol, 3-pentanol. But if we have a carboxylic acid, a separate carboxylic acid with the propionic acid, will form an asymmetric ketone, and when you have the two carboxylic acids reacting together, they will form a symmetric ketone. So what they observe here is that when they have, for example, this carboxylic acid, dimethylpropanoic acid, that has no alpha hydrogen, so the first thing that you realize is that there is no reaction of the two symmetric carboxylic acid. So whenever you don't have an alpha hydrogen, the ketonization doesn't occur. So that's